In the context of manufacturing, deep learning techniques have proven effective for defect detection from images. However, training these models requires vast amounts of labeled data, which can be expensive to collect. This paper proposes a novel domain adaptation approach that addresses the problem of scarce and imbalanced datasets by transferring knowledge gained from an existing source dataset used for a similar learning task. The approach combines a domain adaptation technique with an autoencoder-based data augmentation method to address both the scarcity and imbalance of the target dataset. The proposed pipeline is evaluated using image data for wafer manufacturing, showing superior performance compared to other methods when the number of labeled samples in the target dataset is significantly small and the target dataset is imbalanced. The related work section discusses adversarial learning-based approaches, such as DAN and ADDA, which aim to learn a domain-independent representation by using two competing networks of feature extractor, generator, and domain discriminator. These methods assume that source and target data have the same feature space and sufficient in-labeled target data, and they may suffer from imbalanced class distribution in real-life data. The proposed pipeline consists of two steps. The first step uses an autoencoder-based approach to augment the target dataset for balancing class distribution. This is achieved by generating synthetic data for the minority classes using a Gaussian noise and the latent space learned by the encoder. The second step applies a novel adversarial DA-based approach for adapting the source and augmented target datasets. This approach supports heterogeneous domain adaptation where data from two domains can have different dimensions or different numbers of features. The proposed pipeline is evaluated using image data for wafer manufacturing, showing superior performance against other algorithms when the number of labeled samples in the target dataset is significantly small and the target dataset is imbalanced. Here is a combined summary of the 2 pages. The authors propose a domain adaptation (DA) approach to address the issue of imbalanced classes in wafer defect prediction. The approach involves 2 main steps: generating a classification model and using an adversarial DA method to learn a domain-independent latent space from the source and augmented target datasets. The authors first introduce an autoencoder-based data augmentation method to generate synthetic data for the target dataset. The autoencoder is trained to reconstruct the input, and then random noise is added to the compressed representation to generate new synthetic data. This process is repeated to obtain a balanced training dataset. The authors then describe their adversarial DA approach, which involves 5 neural networks, private generators for the source and target, a shared generator, a discriminator, and a classifier. The private generators map the source and target data to a compressed representation, which is then fed into the shared generator to learn a domain-independent representation. The discriminator and classifier are trained to distinguish between the source and target data and to predict the labels, respectively. The authors define 3 loss functions: the classification loss, the discriminator loss, and the generator loss. The classification loss measures the error of label prediction in both domains. The discriminator loss trains the discriminator to distinguish between the source and target data, and the generator loss trains the generators to maximize the loss of the discriminator. The authors use a mini-batch gradient descent procedure to optimize the loss functions and update the weights of the networks. The authors apply their pipeline to wafer defect prediction, using the mixed WM381 dataset as the source dataset and the WM811K dataset as the target dataset. They address the issues of missing labels, imbalanced class distribution, and varying sizes of wafer maps in the target dataset by dropping in labeled samples, selecting wafer maps of a fixed size, and using the autoencoder-based data augmentation method. They compare their approach with existing algorithms, including fine-tuning-based methods and deep learning-based methods. This research paper presents a novel approach to address the problem of scarce target training data in machine fault diagnosis using wafer maps. The authors propose an adversarial domain adaptation (DA) method that leverages augmented target data to improve the performance of defect detection models. The authors evaluate 6 approaches, including their proposed adversarial DA method, fine-tuning, and vanilla classifier methods, with and without augmented target data. The experiments use the WM811K dataset, and the results show that the adversarial DA approach with augmented target data outperforms the other methods in terms of balanced accuracy and precision. The adversarial DA method uses a GS-GT architecture with 2 convolutional layers, 2 max pooling layers, and 1 fully connected layer. The classifier has 2 fully connected layers with 1024 and 512 neurons, respectively, and a softmax output layer for class prediction. The authors also implement a fine-tuning approach using a pre-trained VGG16 model and a vanilla classifier method with a deep neural network architecture. The results demonstrate that the adversarial DA approach achieves the best results, even with very limited target data, by learning domain invariant features. The data augmentation technique used in the augmented target data significantly improves the performance of all 3 methods. The authors also compare the training and testing times of the different approaches, showing that the proposed DA model can be trained offline and has a low prediction time. The paper highlights the limitations of traditional deep learning approaches, which require a large amount of training data to learn the input-output function of the model. The authors argue that their adversarial DA approach addresses the problem of scarce target training data by using domain-invariant features emerging during the optimization process. Finally, the authors discuss the potential extension of their approach to non-classification tasks, such as optimization, reinforcement learning, and robotic learning, where domain shift and knowledge transfer are critical challenges. The paper discusses a novel adversarial domain adaptation (DA) approach for heterogeneous adaptation, where the source domain has different features than the target domain. The DA is accomplished by training 2 private generators and a shared generator that extract features predictive of the target labels but uninformative about the domain. This approach tackles the problem of scarcity of target training data and does not work well if the target data is imbalanced. To address this, an autoencoder-based technique for augmenting minority classes is proposed, followed by the DA approach. The experimental evaluation on wafer defect datasets demonstrates superior performance compared to other baseline approaches. The paper also discusses limitations, such as requiring at least some labeled data from each class in the target domain and not supporting multi-source domain adaptation directly. Future work involves treating each source domain individually and learning the shared information across different domains for better generalization performance.